Hey everyone, I'm Mirko Baggio. I am the Business Development Director with Zappi Group. I'd like to welcome to this session. Please remember that this session is also being recorded and will be available to watch on demand following this session. If you have any question during the session, please add them in the Q&A. You can find that tab to the right of your screen. With that, I would like to introduce our speakers. I would like to welcome Werner Denk, System Engineer Electric Drivetrain, and Rajvinder Khalsa, Simulation Engineer at ZF Group, that will be speaking today about solving the challenges in the development of electric drive powertrain for compact machine equipment, using simulations. ZF is a global technology company supplying systems for passenger cars, commercial vehicles, and industrial technology, enabling the next generation of mobility. ZF is a strong partner of Zappi Group. ZF has in fact selected Zappi components to complete their product portfolio. So welcome, Werner and Rajvinder. Please take it away.
Yep, thanks a lot, Mirko. We actually are still waiting for Werner. I think there seems to be some issue with him. Did he just log out?
Okay.
Yep, so I think so. There seems to be some trouble with Werner's computer. Yep, he's back.
Here we are.
I had to retry, but I think it's fine. So
Yeah.
let me take over the screen.
Great.
Perfect. Hello, good afternoon, ladies and gentlemen. Welcome to the dev session on this great conference. We want to show you the way of developing an electric drivetrain in a compact construction machine. And especially, we want to point out how important simulation methods are to get the first time right product. The title is a bit long, so let's have a look on the agenda where we broke the topic down and explained it a bit more. We want to start with an introduction of the ZF group and especially of the off-highway part. Then we get to the main part of our session, and this is divided in two parts. The first one will be shown by me, Werner Denk. It's the development of a 48-volt central drive system. I want to explain you the targets of this development project, then showing you the methods of systems engineering that we used to meet the challenges. And then we can talk about I will show you the resulting platform that we built up to solve this issue. And then I will hand over to my colleague Rajvinder Khalsa, who will show you the use of simulation methods and tools to manage the challenges for this development. He will show the solutions that we had in the past, that we use currently, and he will also give you a prospect to the use of simulation tools that we see in the future. After that, we will hold one common question and answer session for both parts. Please feel free to type in your questions on the right-hand side to the question and answer part on the tool. We will try to answer them in one block at the end because we don't want to interrupt the flow of the presentations. So let's start with a few words to my person. As you heard, my name Werner Denk. I am a mechanical engineer, graduated at Technical University in Munich. I joined ZF Group in 2007 and worked in several positions, mainly in function development for agricultural vehicles, and also for some tasks with predictive maintenance and connectivity applications. For around about 1 year, I joined the electrified systems team, and now I'm systems engineer for compact construction vehicles. I'm located in Passau, Germany, Bavaria, where the center of the off-highway part of ZF Group is located. Now, as I said, let's have a short look on ZF Group with some facts and figures. ZF is a company operating worldwide with production locations in 31 countries all over the world, and also development locations in 8 countries. Mainly in Europe, where the center of ZF Friedrichshafen was, and also in North America, where the former its headquarters. And fast growing the Asia Pacific part of ZF with now 42 locations, and also some main development locations. The most important key figures of the company at one glance: we have sales of 48.3 billion euro in 2021, and nearly 10% of this was invested for research and development. Additionally, 1.6 billion euros was invested in properties, plants, and equipment. And here summed up the numbers of employees that you could have seen on the previous slide. 175,000 people are working in ZF. The ZF group consists of 8 divisions. You may know some of them. Mostly common known, the passenger car technology with passenger car transmissions, and also some drive parts. A brand for this is, for example, Sachs. And there also big division is commercial vehicle solutions with transmissions, axles, and for example, communication systems for commercial vehicles as trucks and light trucks. There is also the brand WABCO part of it. And also the divisions active and passive safety technology, former known as TRW, is a big part of the ZF group. And also one of that divisions is the industrial technology division, where the off-highway part is located. Here you can see industrial technology. The off-highway and test systems part had sales of 1.5 billion euro. And the industrial technology is built up also with the fast-growing wind power technology part, and other smaller parts than as aviation technology, marine and special drives, including military technology, for example, and also components. Let's go a bit deeper in the construction machineries, where our product is located. For construction machinery, the guiding principle is Vision Zero that ZF strives to achieve. A world of mobility without local emissions, without accidents, and also without technical failures. For that, ZF invests in developing future-orientated technologies. Despite this transformation, also the current business has a main share with drives for machines with diesel vehicles, and also there the goals lowering fuel consumption and lowering CO2 emissions is a big goal of ZF. For this reason, we have state-of-the-art energy-saving technology for wheel loaders, dumpers, graders, forest applications, and many more. The typical product can be seen on this slide. Here we see the fully automated power shift transmission, which is somehow a standard product for many construction machines, especially wheel loaders, from a wide range of operation weight. It's somehow the basic technology that we offer. Here on the right-hand side, you can see C-Power. This is somehow the technological lead before electrification. It's a continuously variable transmission with mechanic hydrostatic power split. In the middle, you see a well-known product in the market. We offer axles for construction machinery for more than 45 years. Rigid axles, also steering axles, is a big business share of ZF. On the lower side of the slide, you see the electrified products. Here the electric mixer drive, which is a drive to electrify concrete mixers that are based on trucks for all weight classes of that concrete mixers, so that we also can fulfill the requirements from the legislative and also from the customers to improve the air quality and also to meet the driving restrictions, for example, in urban construction sites. And on the right side, you see the product that we will talk in this session quite deeper, the electric power drive for construction machinery. The overview would not be complete without mentioning where the electrification of drivetrains had the beginning. In material handling, we are offering electric drives and components for many years. ZF is a full liner in material handling technology. We have drives for lifting carts that operated manually, up to equipment for use in automated warehouses, for example. We have electric drives in portfolio, electric steering systems, control units, transmissions, axles, as well as safety and connectivity solutions. Here, this example shows a steering system for a front-wheel driven, free-wheel counterbalance lift truck. Here you can have a look on some parts of the material handling portfolio. There are drives with 1 or 2 electric motors for counterbalance lift trucks, and also some drive modules for warehouse applications or for rear-driven lift trucks. Here the steering module, also a version for 4-wheel counterbalance lift trucks, is available, and also the ergo power transmission that is used in diesel engine operated trucks for container applications, for example. The material handling is the point where the partnering of the ZF Group and ZAPI had its origin. We are electrifying the mobility market together in this market segment for many years. We have a cooperation in development of the product, and ZAPI is the system supplier of this product. I think this was a short and quick overview of the dev. And now let's dive deeper in our main topic in the development of the 48-volt central drive system. On this slide, you see a typical application. The components show somehow the end product that we're talking about, but don't mind that. With the outlining, you can see the wheel loader, and if you look at the components of this vehicle, you can see that it differs to other transportation vehicles. It has, of course, a drive, two axles, articulated steering in this example, but it also has a really huge mechanical kinematic to operate the implement, the big shovel. This is operated by a hydraulic cylinder that also has to be operated simultaneously to the drive by a skilled operator. So if you see this product, you see it's a really complex machine. And for this reason, it was decided to use a systems engineering method to do the development tasks. We analyzed the starting situation. The main tasks, you can also call it the enterprise strategy for CF in the construction machinery market. The main task was electrification of a compact size wheel loader. Then also, as important as this specific application is building up a platform strategy for electrification of other construction machines up to 80 kilowatts power in the first step and beyond in the second step. We analyzed the business needs for the project and got additional project targets. It's necessary to be first to market or among first to market because the electrified construction machinery market is developing really fast and growing. So we want to be part of this and be leading with technology. As the second point, staying among technological leadership, we had this position with the power split transmission, also with the CVT transmission, and we want to keep it. So we have a first-time right approach for the electrification. Then additionally, of course, it's some work to pave the road for e-mobility in construction machinery. The construction machinery world is not used to e-mobility. It's just beginning, and we have to get also the products that fit in the current construction machinery ecosystem and cooperate with the other machinery that is used in construction sites. And nevertheless, it's also a point to support ZF's internal transformation to an e-mobility system supplier, which is somehow a driver for the project, but on the other hand, also an additional task to get processes standardized and usable also for the other product lines, for example. From that beginning, there are several strategic decisions that have to be answered. For example, defining ZF's system scope to find the system of interest that can be our the product portfolio that we offer for this market. There are also, of course, the technical challenges, like the driveline layout or, for example, the voltage class. This is somehow an open question, Maybe you could hear the session on Tuesday by Delta Q. There also was a really good presentation about the advantages and disadvantages of the different voltage classes that are in discussion in this product range, product class. And of course, it's challenging to decide whether building or buying the parts, where to spend the invest, where are the components that are differentiating, where is it the best to get a good partner to have the best solution at the end. And it's somehow establishing an ecosystem for developing electrified construction machinery. For that reason, we did some context analysis of the system context of a battery electric compact wheel loader. If this picture looks familiar to you, it's a screenshot from a system model in the modeling tool Cameo. We did an analysis of the subsystems that this wheel loader consists of. Let's go through them quickly. There is, of course, a need for a battery system, for a power supply for the battery electric wheel loader. Then we need a cooling and heating system. Cooling and heating of the driver's cabin, also for the battery system and for the motors, e-drive motor and power take-off motor, and also for the inverters. Then we need 12 and 20 or 24 volt power supply for the the parts that are used from conventional machines, as the HMI parts or, for example, lighting of such a vehicle. Then, as you have seen in the picture of the wheel loader, the hydraulic system is a really big part of such a wheel loader. Then we come to the drive components, e-drive motor, of course. Then inverter for the e-drive, also axles and transmission for the power transfer. Then there must be some controller, some ECU for the electric drive system. And also, as said, the motor to drive the power takeoff that drives the hydraulic system, also with an inverter for this. Then we have the interface to the driver, the HMI interface, and also some vehicle control unit on the top level above the drive controller that manages the whole system behavior. Of course, charging station is a point, onboard charging, off-board charging, some overhead power grid as Scania has shown in the session is not so suitable for construction machines. And last but not least, the steering system is also important for this machine. And with building the picture and doing some analysis on the components, we decided for ZF it's a suitable subsystem range to have that subsystems that in that blue box that you can see on this picture. Let's go to the next slide where we arranged that components in a logical architecture diagram. This diagram here is visualized by colleagues from marketing. We in engineering used another one that did not look so cute, but for this presentation I can use the nice one. The content is the same. If we follow the power lines from the battery Then we see we go to the inverters, to the e-motor, to the drop box, and the axles to the wheels. So the F share is the complete drivetrain that gets power from the battery and drives the wheels on both of the axles. Also with the controller for it. And also following the power lines from the battery, we get the inverter and e-motor for power takeoff for the hydraulics. Then we also drive the auxiliary drives. So this is the scope of ZF. And the other parts are out of our scope. I also will say some words why we decided so. The operating elements as pedals, as levers or displays, and the vehicle control unit, we think that makes the look and feel of the machine, that makes the behavior. And so this is OEM core know-how and should stay at the OEMs. Then the battery also is some point that is really close to the OEM's decisions. In the wheel loader, it's not so complicated to locate the battery. In other vehicles, its packaging may be a big problem. So it's decision of the OEM whether using a big battery pack that lasts with one loading for the whole day, or choosing smaller batteries and some fast charging with charging while lunch and pauses, for example. And there are the components working hydraulic pump and steering pump, where we also said is excluded from our scope. The reason for this is that we see that the OEMs want to produce battery electric vehicle and diesel-powered vehicles in parallel. So it's better not to have much variance in their products, in the components that can be the same in both variants. We come to this in the next slide, where we show what requirements we got from the stakeholder analysis that we did for designing the product. We, of course, used ZF's experience in developing construction machinery. We know the use cases. We have measurements of duty cycles, of course, for the well-known Y-cycle truckload. My colleague Rajvinder will show this a bit deeper in his part. Then stockpile and transportation cycles are also known use cases for construction machines. Then we did, of course, a market research and got the informations and requirements that driving performance of a battery electric construction machine has at last to be at the same level as of a conventional machine with a combustion engine. There are no lower expectations because a machine is electrified. That is not tolerable because that are working machines and they have to fulfill their duty. Then we also got the requirement that the driving behavior of the machine should be kept as it is used to the driver, because especially in the current phase of electrification, they will have to switch between machines. And an electric machine and a diesel-powered machine should have the same behavior. Of course, there is one exception. If there is a benefit and new functionality with electrification, then we have to use this, but only for the reason of creating benefit for the users. Then, of course, a point is ZF strategy. we could have also named it global strategy or world strategy. We all want sustainability and also do some energy saving. And as mentioned before, we got the information from the OEMs that they want to produce the conventional machines and battery electric machines on the same lines in parallel. So it's important to reduce the amount of variant parts. And this has also be kept in mind for the decisions for the layout of the drivetrain, for example. Then let's have a look what our colleagues from simulation provided us. They did some simulations from different layouts of electric machines that were modeled in computer modeling, and they gave us the resulting power lines, and we compared it in this Excel sheet with measurements of conventional machines. This is just an example, so you won't find that machine out in the real world. But exemplaric, you can see the gray line. This is the tractive force over travel speed for this machine. And here you can see with that green solid line of our electric machine that we simulated, we meet the requirement of having the same tractive force for low speed. But then we see we have more power than the compared machine, and also drive faster. So it's not some requirements may be over-engineered with this solution. And so we did some variant of the input parameters for the machines. What also is interesting in this diagram can be seen on the lower part. There you have coasting. The machine is driving downhill, and then the electric drive creates a torque that is braking the machine, that is against the motion, and is used for regeneration and fills up the battery. This is somehow different to a diesel machine. A diesel engine, let's draw it to this sketch, because I did not integrate that line. I think it's okay for first try. A diesel engine has some coasting torque like this. It's increasing with rising speed. And so for the high operation speed, we have to meet the requirement for having the same behavior as the well-known machine, also with the electric machine. And for the lower speeds, then we have the benefit of regeneration torque that can be used for energy saving. Let's go forward and step over the design phase of the component and have a look at what the designers created. Here we have the main components of our electric drive system. It consists of a axle that you have seen in the portfolio. It's the normal construction machinery axle that can also be used with the electric component. And the installation space of the transmission of the conventional machine was used, And there was the transmission designed as a one-stage drop box spare drive that is placed directly to the axle. And here the electric motor is also in the installation space of the transmission, so that it fits in the design and in the packaging of the OEM's installation space that they have with conventional machines. That this system is working, we also need the inverter that was found by our partner Emotion. And also we have the control system. We use the ECU that ZF has in the market for several years, and designed a new drive software for the electric drives. So let's go one step deeper with the electric drive system. Here you can see that our transmission, this one-stage drive, is designed in one size that fits for all electric central drives, for all the e-motors, beginning from 20 kilowatt continuous power up to 80 kilowatt maximum power that we have designed for use in the compact construction equipment. The same electric motor can be scaled in the nominal voltage in the range from 48 volt up to 650 volt. This can be done by adjusting the windings inside the motor, and also adjusting the stacks of metal sheet that are inside there, but without changing the diameter of the electric motor. So this drive system fits to the machine platforms that the OEMs, that our customers have now, and they can change easily up to the electrified versions. The electric motor only changes in the length, and this is the less critical dimension where we can have installation space for the system. To get the system running, we need the inverter, and they could be found by our partner SAPI, the part Emotion. We found an inverter for 48 volt, for 96 volt, and also for 650 volt, which are the main voltage levels that we decided are the right levels for the first step in electrification. For this reason, Emotion also designed a liquid cooling interface to the inverter, that the inverter fulfills the requirements of lifetime and reliability that we have in construction machinery. And one additional advantage of this product is the change of operation mode. The same operator can be used for powering the EPTO drive and also the drive motor. Both motors can be connected to each to the same inverter. We need two similar inverters with the same software, and one can be connected to the EPTO and one to the eDrive without additional variants, except the software configuration. So this is also a really good solution for our strategy to get standards that enable high flexibility of the products that we offer to the customers. The inverters have currents up to 900 ampere in the 48-volt version, which enables us to fulfill the requirements for attractive torque. So this is a really good match for the product. And so we could define the resulting product, the e-truck ECD20, as the whole product name is. That starts electrification in the electric compact wheel loader, as said before. And we also did some additional analysis meanwhile, and have seen such a drivetrain would also fit, for example, in an electric compact dumper, and some components of the system would be suitable for use in compact excavators. So if, we have a good starting point for going forward with electrifying the construction machines. With this overview, I want to end my presentation, and Rajvinder can take over.
Yep. So let me just share my screen with you so that you can just see it. And so yes, please let me know. Can you see the screen yet?
Perfect.
Perfect. Okay. So thank you guys for joining us here for this particular session where we are going to talk now, where we delineated the challenges of developing a compact compact equipment using electric drives. Now, I would, as the second part of the session talks about the challenges that or the solutions that we found using simulation, I will be taking up this particular topic. Thanks a lot, Werner, for delineating these challenges and showing us the entire system, explaining how things work. I hope for the attendees, it was pretty clear to understand how it worked so that this entire second part of the presentation would be more understandable. Okay, so building on Werner's presentation and whatever he showed, now let us try to have a look at the solutions of these particular challenges. We need to keep in mind, particularly when talking about these solutions, is that for us, the major challenge was to have a product quickly onto the market, and at the same time making sure that we learn at the same parallelly from our mistakes that we were making during the entire production. Although the product is perfectly successful, it is definitely successful, it is an ideology at ZF to keep on learning from your mistakes. So basically, this solution or the solution that we generated or we found using simulations, we are constantly developing that, and we are trying to improve on that. Before we jump into the entire solution part, and before I start showing you the simulation part of it, I would like this opportunity to properly introduce myself. I am Rajvinder Khalsa. I have been working with causal and acausal 0D 1D simulations for past few years. I initially started with simulating batteries for electric aircrafts. Before I joined ZF as an intern and a thesis candidate, where my focus was majorly simulating electric systems for Formula E race cars. Finally, following my work for the race department, I joined the off-highway segment, over where I'm working with Werner and the team in the pre-development phase of electric drivetrains for off-highway products such as wheel loaders and compact equipments, what Werner currently introduced. So that is enough about myself. What Werner explained, or what basically the schematic that you had seen, if you can, we will get back to the schematic again. Developing this compact equipment is a challenging task. Now, when we talk about these challenging or complex systems, we need to understand the basic fundamentals of how these systems are made, or in general, to understand why such systems are complex. Although, for many of people who are attending this conference, they might be pretty abreast with the wheel loader or the off-highway segment. I would still like to show over here something known as a truckload cycle. Don't worry about it. This particular video does not have any audio, so don't worry if you think that your speaker is not working, because as it is, there is no audio. So if you look at the entire working of the cycle, so the loader basically goes to a pile. Over there, it fills its bucket. And from there, after filling the bucket, it drives reverse. And then from there, drives towards the truck. Now, in this particular motion, or in the set of motions, if you look at it, the basic idea or the working of the system is complicated in that not only the loader has to work or move forward and backward at the same time, it also, let me just play this again so that it is easier for all of us to go through it again. Yeah. So it is not only required that the loader moves backwards and forwards. At the same time, it needs to perform this complicated task of filling the bucket up and hoisting the entire system so that it can dump the entire material in the truck. When you're electrifying any system that has two operations or multiple operations happening at the same time, it is unlike a passenger car wherein the main task of the electrical system would be to just drive the vehicle forward or backwards. Over here, there are definitely other auxiliary systems, but that is one of the major differences that you need to keep in mind when working with such complex off-highway equipment. Getting onto the schematic, this is the same slide that I stole from Werner, actually. So if you look at it, it looks really cool. As Werner explained, following the power lines, the battery is connected to the inverter for the electric motor that works or that operates the power takeoff or the PTO. At the same time, there are battery lines that basically connect to the inverter, which is then connected to the traction motor. The traction motor is connected to the drop box, which then is connected to the axle, which drives the wheels. The EDCU, or the electric drive control unit, is responsible not only for the traction system, that is the inverter 1 e-motor drop box axle system, but at the same time, it also takes care of the electric motor hydraulics. In addition to that, the systems that are not directly addressed by ZF, that is the battery system, the VCU, and other auxiliary systems, although they are not directly addressed by ZF, we at ZF, we think in integrated development. So for us, it is important to have a larger system overview than to just focus on our part and just provide that and just get done with it. So that is something which is important. That is that we focus on systems rather than subsystems or just simply components. Summarizing the challenges that Werner explained in his part of the presentation. So basically, we have these 4 main challenges in our crosshairs. We need the same performance, at least the same performance as conventional wheel loaders, or basically conventional drives. We need to make sure that the architecture or the entire system that we are developing, it is scalable. That is, for it could be adapted to different voltage sizes, different motor sizes, and different gear ratios. In addition to that, as I said, it is important for us to have an optimized system and not just focus on the components. That means that we would not like to be penny wise and pound foolish, but we would like to focus on the entire system. And finally, the buy or build component analysis. That is, does it make sense, or the components that are already available, that are, for example, the systems that SAPI Group provides, if how those systems suit best with our system, and how can we use that so that we can reach the market as soon as possible. In addition to that, we also need to understand that when we talk about conventional drives or the same performance as the conventional drive, it is not just about power, it is not just about the torque or the load that the vehicle can take. It is also considering the work duration that a conventional vehicle offers. That means that in the conventional vehicle, if the entire work hour was 8 hours with a 16-hour rest in between two shifts, or basically between two working days, the electric drive needs to provide this particular performance as well. Additionally, when we talk about these challenges, like Werner mentioned, it is important to make sure that we do it quickly and accurately at the first time. Now, we did this accurately, we did it quickly, but there are always lessons to be learned. So this entire simulation process, which I am about to explain right now, it has been divided into three parts. So the first part focuses only on the past, or basically what we did. Then we talk about the present, or what we are doing and what we have learned from the past, and how we think that this entire what we are doing right now would not only support these compact equipments, but at the same time take forward the entire industry as a whole, or thinking about how it would improve all other sectors that ZF works in. And also the future, where we think from our side what is the direction that needs to be taken when we talk about reaching this sustainable reduced energy or zero emission phase or target. So let's jump into the past approach. This is a very rough and small summarization of what we did in the past. So there are basically three parts that we focused on. The definition. The first is the definition, that is just basically thinking about what is our target. Now, the target is, as I explained, these challenges. Let us take one target, for example, as the same performance as the conventional drive, or maybe focusing on scalability, something like that. So that is the first part of the approach that we used. That is properly, concretely defining what we wanted to achieve. The second part of the second step in this approach was the collection. Now, in this SAPI group, during the initial development phase and throughout thereafter, they have helped us with developing our system so that we don't have to reinvent the wheel. So that was really helpful of them, like using inverters from InMotions, and we got the data from InMotion. They were constantly in exchange with us, and we were able to send our results, take their knowledge, and integrate the system as quickly as possible. Following the collection phase, wherein we use our past learnings, we collect the current data, and at the same time collect the data from our partners. We get into the final phase, which is the calculation phase, wherein we actually think about how we can, if not extremely sophisticated, simulate it, but at the same time reach a very accurate and plausible result. So that was the third part. These three steps, I'll explain it using three or four basically examples. So how we went about it. So first part is the thermal behavior, or when we were thinking about the thermal performance of a motor. So if you look at it, this is basically a plot of the temperature profile that a motor that is across the length of a motor, and the temperature in y-axis. So the target was basically to understand what temperature is reached at which all sections or cross sections of the motor. The catch over here was that since we are developing this equipment for the first time, or it is an initial development phase, you need to reach certain assumptions and take educated guesses so that you reach your result with the greatest amount of accuracy, and at the same time those results are verifiable. As a result of which, we took some assumptions over here, as you can see, that with the efficiency and the percentage of losses that can be conducted over the input shaft, and overall loss, etc. The limitation over here was that we during that time were focused more on optimizing the component and we had more of a component purview rather than going directly or jumping into the system purview. Following this, if you look at the electrical analysis over here, we had more idea of the entire system, or we had the system in our focus, in our crosshairs, and we use this electrical analysis to decide the electrical dimensioning of different components. So these simulations over here were basically made for different load cycles. As Werner might have shown, this diagram might be familiar from Werner's slides, for different load cycles across time. And at the same time, we looked at what sizing of each component do we need. Additionally, if you look at it, that the peak torque of the motor that we were using, or we wanted to understand if it can suffice our needs, we took the motor and inverter into consideration. So basically focusing on the immediate subsystem. Following this, like kind of the point that I want to drive over here, particularly with this calculation or this part of the simulation, is that focusing on subsystems and developing these concepts helped us realize what we actually need to focus on in the coming future and how we reach our target quicker. Although focusing on individual components and individual subsystems does lead to accurate results, but that is more labor intensive. It requires experts to be actively participating in the entire development process, and then it basically slows down the entire development process as a whole. So our target is, like I said, to reach the market first, reach it accurately, and make sure that the product is perfect, but make sure that it comes in quick as well. This is another example of the NVH analysis that we did. And again, we focused on the subsystem of motor and gearbox. Following the lessons that we learned from the past, we come to the present. So in present, as you could remember, we had three parts. So one was definition, the other was collection, and the third one was calculation. So from that past, we learned that is not all that we can do. We need to do something more, and we need to reach a more comprehensive approach. We need to use a more comprehensive approach to solve our challenges. So we came up with this 4-prong approach, or a 4-step approach, wherein we have the definition as always, wherein we define our target, following which we go into the quantification phase. That is, we focus on the system, try to quantify the targets in, let us say, a power versus time, or a speed versus time, or a torque versus time profile over the lifespan or over a specific time duration of the vehicle. So not just focusing on one component and how it would perform for a certain instant or a certain operating point for that matter, but focusing on how the entire system or how the entire vehicle would perform over a span of, let us say, a truckload cycle, the video of which I showed in the second or the third slide. Or let us say, for the example, stockpile cycle or a transport cycle, or what would happen when I keep on running those cycles one after another, or a mixture of them over a span of, let us say, 5 years, 6 years, what would be the performance of the vehicle? So that was important for us to also take into consideration, to extrapolate our vision and push the vehicle. What would happen if we push the vehicle to its braking limits? So that comes in the quantification phase. The data or the calculations or the understandings that we gather, the data that we gather in the quantification phase, we use this data to run our simulations. The simulations, as compared to what we did in the past, are more integrated. They are more, top down, rather than just focusing, going from down to top. That is, that we not only focus on individual components, but we focus on the entire system, and not only stick ourselves to just one software, but take a mixture of software, look at the interaction between all of them, and use that entire knowledge that we get and try to optimize the entire system. So that is the target of the simulations. And finally, following the simulations, we get into the validation. The validation over here, for those of you who are pretty aware of how things work, is not the same validation as what you might find in a technical or a traditional, how do you say, approach. In this, you would also, this validation is basically to optimize the simulation. Okay. So just a second. I think my laptop is about to die. Yep. That is taken care of. Sorry for this particular issue. Okay. So now getting on to the first part, that is the definition. Okay. So the definition, as you can see here in this particular slide, that our target was to reach the same performance as the conventional drive. And so we have this conventional drive profile that we had from initial drivetrains that we had provided, or the initial equipments that we had provided. You look at the peak performance or the peak traction that is required. Over here, what I would like to emphasize is that the peak traction or the peak performance of the vehicle is in focus, and not just the motor or a particular subsystem. Additionally, if you look at it, there is, you see the performance or the behavior over various gears with our conventional drive that we had used then. So the advantage of this particular system is that we are focusing on a battery to wheel analysis and not just on certain subsystems. Additionally, we are focusing on an integrated solution, and the target of the entire approach is to optimize the system rather than just optimizing certain subsystems or a component. Okay. So once we overlay, once we use this in the definition phase, once we take the performance of the conventional vehicle and overlay the motor profiles, we see that we have a region of overlap between the peak profile of the motor and the continuous profile of the motor. This overlap region basically helps us understand when to actually go into the shifting phase. That is, when should a gear shift happen? Conversely, if I were to decide the point of gear shift or the vehicle speed at which I would like to shift my gears, I can see which motor profile would fit this particular range the best. Now, this is the approach that you take. These are the knowledges that you gain in the definition phase, which then are used further on in the quantification phase. As I explained, quantification is collecting data from the short Y cycle, or basically the performance or the behavior of the vehicle in any of the cycles, the data which InMotion kindly provided us of their systems, then the knowledge that we had, the knowledge that was largely available. You collect that data up, you use that data to build a power or any sort of a profile against time, which can be reiterated over and over again, and which can be fed into a simulation environment. The advantage of doing this, as I mentioned, is the possibility to push your system to the limit, which in reality might not have been possible, or if you were to focus just on a part of the system, it would have resulted into a successful system on the component level, but might result to failures on the system level. So if you could see, we are done with part one, and that is the definition, and then the quantification. Now we go on to the main crux, that is the simulation. Okay, so the simulation part. Now, in the simulation, this is the main crux of the entire presentation, or my part of the presentation. You have the system requirements that were decided during the definition phase. You additionally have the data that you collect during the quantification phase. So these two system requirements and the performance requirements per se are collected and are gathered using Cameo like what Werner showed, and additionally Code Beamer to manage requirements, and Excel as it understandably, because it's apparently one of the most powerful tools. So you manage these system requirements. You take these system requirements, work them out into a systematic power profile or any sort of a profile over time, as I explained in the quantification phase. You feed those power profiles into a driver model. So the entire simulation environment, which is built using multiple softwares, that is MATLAB Simulink, Timula, and also integrates many FMUs, hence it has to be FMI adherent. These performance or the power profiles are fed into a driver. Now, the advantage of building a driver in the simulation environment, we found out, is not only to have an ideal driver, but at the same time have an aggressive driver which can push the system to its breaking point. And the minute we reach the system's breaking point, we understand how our controllers are reacting to that limits when we reach it. Additionally, this driver is not going to get tired. So if I ask the driver or simulate the cycle for, let us say, 4,000, 5,000, or maybe even 30,000 seconds non-stop, it can do that. So that is the advantage, like everybody knows, of the simulation environment. From the driver, it goes into the control system, that is the DCU or the driver control unit, and additionally the vehicle control unit. The controllers over here decide on the control logic based on the information that the driver provides. That is, if a speed is reached, or if a torque or a power point is reached or not. Based on that, the controller would decide if it has to switch on to if it has to switch from the first gear to the second gear, or does it have to reduce the torque because one of the components is at its critical rate, that is maybe go into derating phase. Or let us say if the battery is close to its end of close to its cutoff voltage, it can derate the battery and at the same time control the entire system. So the controller provides the torque request over to the electrical, thermal, and mechanical system. Basically, over here, the controller is not only taking care or like kind of giving commands to the thermal system. The thermal system, the electrical, and the mechanical system, they communicate with each other as well. The point that I'm driving over here is that, again, we have the system in our main crosshairs rather than just one single component. So when we talk about thermal system, then it is basically the entire thermal system of the motor as well as the gearbox and the battery. If we talk about electrical system, if I talk about the battery, the inverter, and the motor. The data for these modelings are obviously obtained from other stakeholders who provide these systems, and also from the OEM, depending on their share of the product, or their share of the project. Additionally, if you look at the mechanical part of it, then the mechanical part basically tells you how the vehicle would perform as a whole. What we use is basically ANSYS software or individual component, exact component simulations to populate the parameter files for these three systems, that is the mechanical, electrical, and thermal. The advantage of doing that is that you have a very accurate system already modeled inside your in your simulation environment, but it gives you the freedom of not having to use it all the time, or you can use this complicated or transient simulations to parameterize your simulation environment, but then use, let us say, a quasi-static simulation approach to simulate the entire vehicle, which is basically quicker. Following the three systems, you enter into the vehicle dynamics. From the vehicle dynamics, you basically have an output or system analysis interface, wherein the analysis of the battery, the inverter, the motor, gearbox, and also the system sizing, performance, everything can be one. Looking at this simulation interface that I've shown over here. So basically, if we could recollect the four challenges that we had, that is same performance as the conventional vehicle, then same performance of the conventional vehicle, scalability, system over component, and buy and build. So all of these 4 challenges can be addressed or have been addressed by this overall system level simulation interface. I can take care of scalability or basically buy or build analysis by populating these 3 systems, wherein I populate the component files from the data that I get from the stakeholders and also from the data that I or we decide to enter into these subsystems. I have a system performance in my crosshairs or in my side, and at the same time I can manage these system requirements as I please. And additionally, if I talk about scalability, this particular simulation interface is infinitely scalable. I can scale it to any other platform. I can use this particular approach for simulating any other vehicle as well. Till now, what I showed was everything theoretical. Now, let us see if we walk the talk. So this is the simulation interface that we are using right now. The input over here consists of the input, driver, and the control. The electrical subsystems, as mentioned, are basically 2. That is the PTO, the power takeoff, and the traction motor. Following which I have a mechanical subsystem, which consists of the gearbox and the driveline. Following which I have a thermal subsystem. And the thermal subsystem has, if you could see, it has connections all the way to the electrical subsystem, that is the PTO and the driveline, and also to the main input. And if you look at the gearbox, it has again the connection to, so basically if you look at the mechanical subsystem, it has the connection to electrical subsystem. Additionally, we have a system analysis interface, which helps us understand what are the currents, the voltages, or the temperatures that we are reaching. What is the shift? How is the shift logic working, or how does it look like? If we are shifting at the right time, if there is a massive drop in the traction force that we have available on the road, things like that. You might notice that there isn't, I haven't shown over here the vehicle subsystem, because that is something that the OEMs generally like to keep it under wraps. And as a result of which, we are not privy to show that right now. But overall, the thing that we basically from our side show is an additional vehicle subsystem, which then accesses all these information and then provides the basic system performance data that we need to reach a very educated decision. Looking at certain results that we generate via this simulation, one of the targets, or one of one of the challenges that we had while designing the system is the cold start performance and its remediation. So what we did, or what we thought about, is simulating the entire system at 0 degrees Celsius, looking at electrical losses that we have at 0 degrees Celsius. The idea that we had was to simulate real world scenarios as closely as possible, and at the same time try to find out a method or a trick, so to speak, so that we can end this cold start phase as quickly as possible, so that we can bring the entire system temperature to its desired temperature as quickly as possible. In doing so, we run iteratively a short Y cycle for, let us say, 1,000 seconds as an example. And the advantage, per se, of these simulations is that you can not only look at the derating strategy if we are kind of critically pushing our system at 0 degrees Celsius, for example. We have the opportunity to optimize the entire system, because we not only have the currents and the losses in the motor, but also we focus on the temperatures at various points, for example, in the inverter or in the driveline for that matter. And additionally, we have this opportunity of thinking about scavenging heat from one part of the component and passing it over to the other part of the component, wherein so that we could maybe somehow use the heat generated in one part to heat up the other part, so that it can reach its optimal working temperature. Additionally, it gives us the idea or the possibility of testing if using the charging phase, which would happen at the night, to maybe bring the entire system to a certain temperature before I start with my working. So that is also an additional advantage that we had while simulating these results. So coming back to this overall overview, we are finished with the definition, the quantification, and the simulation as I'd shown. Now let's get on to the validation. Thinking about the validation yet again, the idea of validation is not per se to jump from simulation and then going into manufacturing and then trying to validate your product or trying to see if it is performing as you want. The idea is basically of this validation is in the simulation environment to use the outcome or the results of the simulation, trying to mimic on the test bench, trying to mimic them on the test bench or in the field. The deviations that you have from this particular testing, you feed those deviations back into the test bench area and read and try to simulate them again. That is, that you try to couple the simulation and the testing in such a way that at the end of the day, it can improve my simulation interface as a whole. The purpose of being so simulation focused, or the idea that we at ZF have of trying to improve our simulations to such a larger extent, is something that I would explain towards the very end of the presentation. But it is always, in my opinion, or in our opinion, easier to simulate something than to simulate something and check there in beforehand if there are any issues, than to manufacture it and then end up wasting your resources for it. So the present is complete. That is, we are finished with the definition, quantification, simulation, and validation. Going over to the simulation ecosystem, let me just summarize it. How does it look? So it is the start, then we get in definition, quantification, simulation, validation. The validation and simulation is iterative, and then you reach the target. The data set, or the data that is required for each of these stages, is pretty self-explanatory, that you need requirements, the data from stakeholders in the definition phase. In the quantification phase, you need data sets for the model, the power profiles, the dimensions, and the characteristic maps or the performance maps. In the simulation phase, you need to make sure that you choose the right software and standardize the code, and as well as the interface. But what additionally we need to focus, or what we are focusing on, is that there has to be a unanimous or a unified approach when choosing these datas for each step and feeding those datas. That is, that the code should be standardized, which means it should have always a standard nomenclature, a standard methodology of coding, and a standard interface that is used, which is reproducible, which is adaptable, and which is scalable. When we talk about system definition and requirement, we need to make sure that the system definition and requirement are such, or other way around, the code developed is such that it is in always in congruence with the system definition and requirement. And at the same time, the data set and the characteristics map that we have, they should be in congruence with the system requirement, and at the same time, the coding and the simulation interface. The reason that we think that it is very crucial or critical to have such an integrated approach is, we see for the future, or like the simulation for the future, to be digital twin. That means that we think that we need to have an opportunity wherein we take the entire simulation, put it on a virtual cloud interface, so that not only the owner, but as well as the participant can access this simulation, use it to optimize the simulation entire interface, and reduce or accelerate the entire development process. That means that based on a use case definition, we reach reliability in the shortest time frame possible and with the least number of iterations or with the least number of times that we step back to a step before where we have reached. That means that if we have a use case definition, the system design and the requirements in the tasks should be so decided that everything on the right hand side of the V is plausible and is reachable at the quickest pace possible. This is what we think as the future of simulations. And I think with this idea in mind, I would like to end my presentation. And I thank you a lot for your attention and would now really appreciate or we would like to now ask you people to put all your questions in the Q&A chat on the right hand side and let us know if you have any questions. So thanks a lot.
Yes, thank you, Werner and Rajvinder, for this very comprehensive presentation. So I was thinking about this very nice tool and simulations, and complicate probably because it looks in some ways very complicated. You need expert people like you to make it possible and make it run properly. But in the other way, this tool looks amazing. So I am just thinking how many times the customer, after maybe you give to them some specification about your system, they come back to us and say, well, instead to have, I don't know, the liquid cooling temperature 60 degrees, I can ensure to you just 65 or 70, how the performances of the vehicle will change. And I think with these simulations is, let's say, quite easy to give an answer that is very comprehensive. In the old days, this was not possible to give an answer or to predict what will be the impact in this kind of situations.
Yes, true. That is extremely true. So there is also this one issue that we face when we depending on the last slide that if you look at the last slide that I presented about digital twin, there seems to be a sort of a black curtain between the stakeholders of an entire system or an entire product. So what happens is that you have the simulation interface. The simulation interface tells you something. The manufacturer or the OEM or the person who is manufacturing the entire system would believe the simulation, try to validate it and verify it as much as possible, develop the product, give it to the OEM. The OEM would sell it to the customer, and the customer would then take the product away. So the data that you get from the field is always lost, because there is always this gap of communication between the OEM and the customer, or many a times the data is not sent from the customer over to the main manufacturer. What we see from digital twin as a very big solution or as a very big option to take care of this challenge is that digital twin has this integrated cloud approach, wherein not only the OEM, the owners, but all the other stakeholders, which might also include the final customer of the product, would be able to access it, feed their data inside it, and then help us optimize our simulation interface so that when we get into the next version or the next iteration of a particular product, we can reach our culmination in the shortest time frame possible.
Yeah. So I have another question. This model is, as I said, quite complicated from my point of view. And is it? Did you got already the request from some OEM to get the model and try to be integrated in their vehicle model? So in order to see the full vehicle model in the end.
Yeah, we are actually working on parallel projects which require or using this entire approach, or for which we are also developing this approach. But unfortunately, we cannot due to confidentiality issues, we cannot state their names. But definitely, that is something that more OEMs and more customers our customers are excited about. They also would like to learn simultaneously and try to deliver the most optimal solution that is available.
Yeah, I see.
Yep.
Okay, so if there are no any other questions, I think we can close here this quite long session today. But I think was well spent this time. So thank you both of you, and I hope to see you soon. And I will leave you to go for your dinner.
So it was really nice being part of this conference. Thanks a lot.
Thank you.
It was a pleasure.
Yeah.
Thank you.
Thank you. Bye.
Thank you. Bye bye.
Goodbye.